All right, so, I'm Mike Schliep. This work was done in collaboration with Eugene Vosterman from Kansas State University and my advisor, Nick Hopper. And so in this work, we are focusing on designing a protocol that provides consistent, synchronous, group off-the-record messaging, and we call that SYM-GOTR. The goals that we want for this consistent group off-the-record messaging are that of your normal messaging protocols. So we want message confidentiality, integrity, and authentication. We also want to limit the scope of compromise, so we want forward and backward secrecy. But for off-the-record messaging, we would also like some deniability, which apparently is a heated subject. But so we want deniability. But when it comes to groups, there's a few additional properties we want. We would like to maintain participant consistency, so that way, before conversations progress, all users agree on who is part of that conversation. And additionally, we want transcript consistency, so all users agree on the messages sent before they send more messages. The system model that we're targeting with SYM-GOTR is that of instant messaging. So this is it assumes a central server that's going to route messages for us, and with online participants. So for example, XMPP or your developer meetings or something, maybe a small IRC community. The participants need to perform a small set of transactions or operations. They need to be able to set up conversations. They also need to be able to have dynamic groups where they can add or remove users without having to restart the protocol. I leave the adding or removing part to the paper. They also want to broadcast messages so that they can actually communicate. And the threat model we're concerned with in SYM-GOTR is that of a compromised server and possibly compromised participants. So existing work, right, you've probably all heard of Signal and WhatsApp and Threema have this end-to-end security. They generally focused on the two-party case and then bolted on the group setting afterward. There's been some recent literature that has looked at how the group messaging is affected in their designs and protocols, and has identified a handful of vulnerabilities, one of which is a participant inconsistency vulnerability, where a malicious participant, Eve, can convince the group of Alice, Charlie, Bob, and Eve, or can convince some of the group that Bob isn't part of them. And they can still make forward progress with the conversation. Additionally, a malicious server or compromised server can affect the transcript consistency of the conversations by simply deleting them or sending them out of order, and it's not verified by the clients that anything went wrong. So in terms of academic literature then for providing these secure group off-the-record communication protocols, there's only a small handful, and none of them are practical for use right now. They have some serious limitations you can see the paper with. So now for SYM-GOTR, how do we provide these strong consistencies in group communication? Well, a quick overview. The first thing that you do is when setting up a conversation, all parties have to create pairwise, deniable, secure channels to each other. After that, they perform a participant consistency check to make sure they all agree on it before sending messages in the conversation. During this consistency check, they also share some symmetric key material that'll be used. Then when sending a broadcast message, they use that symmetric key material to encrypt it and send it along. And after every broadcast message, they perform a two-part consistency check before processing any more broadcast messages. The first part is to make sure all users have seen the message correctly and that it is authentic. And the second part is to identify any misbehaving users, trying to cause inconsistencies in the transcript. So a little more detail now. I'm going to go through the setup and broadcast phases of SYM-GOTR. So when we're going to look at a group of Alice, Bob, and Charlie, and our servers up in the top there. All messages are routed through the server, even the peer-to-peer ones, but I'm not going to draw them that way. So Alice wants to set up this group with Bob and Charlie. Out of band, they agree to the group. So for example, with XMPP, the multi-user chats, they just use what the server tells them is supposed to be the group. So they set up Forward and backward secure deniable authenticated channels. The details of that are in the paper. We used the Naxos key agreement for it. You could just replace it with OTR if you want. The first thing that they do after they have all set up these secure two-party channels now between each other is Alice will generate some symmetric key input material. She will then generate ephemeral signing and verification keys. And additionally, she will generate a value or compute a value for her view of the group. This is her group view. It takes as input a hash, or it takes as input the session identifier and the list of users in the group. She then shares the symmetric key material, her ephemeral verification key, and this group view with Bob and Charlie. They do the same thing, generate their own key material and group view and share that with each other and with Alice. And all users then can compare their group views to make sure they are consistent before progressing. If they're not consistent, they terminate the protocol session. So for broadcasting messages, we're going to look at the case of Alice sending a message to the group. So to broadcast the message, first, Alice will compute a symmetric encryption key, given a key derivation function with the inputs of the session identifier, the sender's identity and symmetric key material, and then additionally all the identities and symmetric key material of all the other users. So this is a symmetric key they all can compute. She then uses authenticated encryption to encrypt the message under that key and sends the ciphertext to the server. The server's in charge of broadcasting it out to all the users. Every user can then use the authenticated decryption to verify that they have received the ciphertext correctly. It doesn't provide authentication, but it provides integrity that it wasn't modified in transit. So the users do not display this message yet. Next, they perform the first phase of the consistency check. So from the point of view of Alice, she checks that the ciphertext is the one that she uploaded to the server. She then produces a digest of the message, which is a hash function of accept, the string accept plus the ciphertext, or the string reject plus the ciphertext. So if it's not the ciphertext she uploaded, she'll use reject, but really she'll probably just always use accept. Then she uses that ephemeral signing key from before to sign her digest of the message. Over the deniable two-party channels, she sends the digest along with her signature to Bob and Charlie. They do the same thing. They produce an accept digest if the ciphertext successfully decrypts, and they reject it if the decryption fails. So after this phase, they're able to verify that they all computed the same digest of accepting the ciphertext, and they can verify the signatures of the ciphertext. Now they can display the message. However, it could be the case that Bob is malicious and decides to tell Alice to accept the message and Charlie to reject the message, causing a transcript consistency error. To deal with this, then, we want to identify Bob. The trivial way to do this would be for Alice to share all of the signatures she has received on these digests over the two-party channels, and all other users would also share the signatures they receive. However, this becomes very expensive because it's linear in the size of the group to share this for every message. So we make a simple optimization, assuming that most conversations are benign and there's no malicious participants. So the optimization is we simply hash the digests and signatures of all the accepting digests, and then we attach on all the reject digests. So for the most part, it's going to be constant size then. And then to provide forward and backward secrecy to these conversations, during this stage we also share new ephemeral symmetric key material and verification keys. So it's not just important to have a secure protocol, we also need a usable implementation. We implemented this as a Java library and a plugin for the Jitsi instant messaging client. To see if it was performant, we ran some tests with a $5 a month Linode server. This server acted as our XMPP server. It ran the standard eJabbered software. And then we ran 40 clients across 8 university machines. We argue that 40 is on the large size of what you're going to do for private, mutually authenticated conversations, so these off-the-record conversations. We have more reasons on why that, or more reasons for that argument in the paper. And then we compare it to the WPES paper, which we refer to as BD-GOTR for its use of the Burmeister-Desmet key agreement. So in terms of setup now, the WPES Burmeister-Desmet protocol takes around 6 seconds to set up a group of 40 users, where in comparison SYM-GOTR is just over 1 second. We also compare it to, or we also analyze IRC logs from the OpenStack project, and most groups are around 5 users, so at that case, we're easily less than a second to set up, around 200 milliseconds. In terms of broadcasting messages now, SYM-GOTR is slightly more expensive because we have this strong 2-part consistency check. However, again, with 40 users, it's just over a second, and the messages were not sent that often. Messages were sent about every 6 seconds in the IRC logs we analyzed. And for 5 users as well, we're down near 200 seconds anyways. We're under 200 milliseconds to display the message. So the key takeaway that we have now is we propose SYM-GOTR as a secure messaging protocol with strong consistency guarantees by using a participant consistency check before sending messages and the strong 2-part message consistency check after every message. And it's practical with our Java implementation. You can find the source code in GitHub. So, any questions?
Any questions? Yeah. Many.
So, if one of the members of the group is offline, does that mean no one can see any messages? Or if I misunderstood?
So in this work, we are focusing on online participation only. So these are, your IRC meetings and things. We have some coming up work that's in the mobile messaging model, and I would love to talk to you about it offline of all the challenges of that.
Hi. Maybe it's a silly question, but you mentioned IRC is one of the use cases. Does a net split make any problems? Like when people join back, or when they're like, because I've had meetings where we're having it on IRC, and then suddenly it turns out half the people are on one server and the other half can't see those messages.
So this assumes that a single server is doing the routing of messages. If your servers are communicating, you could do it with multiple servers, but this also assumes that the server is going to try to send messages in the same order, and IRC doesn't always try to do that. So we only support XMPP but in the plugin case. But if you can modify your IRC server to try to provide that consistency, then it'll work.
Any more questions? Yeah, I have one final question. You do rely somewhat on a central server doing some of the routing and of the messages.
Yeah, just to send the message.
Right, but is there any way that you can use that central server to do something in terms of consistency without relying too much on it? Or is it, I mean, it seems like if you have some component like that, maybe that could help you to make the system more efficient.
Yes, so in the mobile messaging case, we do rely more on the central servers to do some, provide a little bit of consistency. But the trouble is we don't want to trust the server for a thing. Like at some point, it's going to be compromised if we're ever targeted. So we'd rather just not rely on it.
Thank you. Let's thank the speaker again.